All right, so we've talked about methane, ethane, propane, and butane, so 1 through 5. I'm sorry, 1 through 4 carbons. This is the fifth carbon, which is a pent, like the Pentagon is five-sided building. Pentane is 5 carbons, and there are 3 different isomers. All right, you got pentane. All right, sometimes you'll see this as N-pentane, N meaning normal, meaning it's a straight chain. Okay, then you have isopentane and neopentane. I don't necessarily want you to know these names. These are what's called common names. These names under here are the IUPAC names, the IUPAC. You guys learned how to do naming in Gen Chem. All right, there's a very specific set of rules that we're going to learn how to name. All right, you don't have to memorize these because you are going to learn the rules. And once you know the rules, you can look at any alkane and you can name it. Okay, but these are all different isomers of propane, where I take one of the methyl groups and I put it on this carbon right here, which is that molecule. Now, this is kind of interesting. Let's kind of go over this because some people sometimes don't realize this. Okay, I'm going to draw out these 5 carbons, 1, 2, 3, 4, 5. All right, let's say I take this carbon here, carbon A, and I put it on carbon B. So that structure would look like that. Okay, so those 5 carbons, 1, 2, 3, 4, 5. Let's now take carbon A and put it on carbons, let's call it D. C would kind of get confusing. So that molecule would look like C, 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 C. These look like different compounds, but they are not different compounds. These are identical to each other. Same compound. Okay, so that's why I tell you don't be fooled by structure. If I were to take this molecule right here and I were to flip it 180 degrees, it would look like this molecule. All right, just kind of flip it over, and it's this molecule. All right, it's kind of like I'm grabbing that carbon and I'm bringing it over this way. I'm not spinning it. Actually, you could actually spin it, kind of, but that's on the bottom. It's just kind of flipping it over. So these are the same molecules, okay? So whether I draw it like this, or like this, or like this, these all 3 are exactly the same molecule. They're all 2-methylbutane, or isopentane, okay? Another possible structure would be to take maybe this carbon and take this carbon and put them both on that carbon right there, and you get this carbon. The formula is still the same, C5, H12. All right, nothing has changed. They're all the same formula, but they're all different isomers. All right, so that is pentane. And now here are the remaining 10. All right, there really is no reason to go. I mean, hexane is going to have a lot of different isomers. Imagine how many we have in decane in 10 carbons. We have a lot of different isomers. We're not going to go through all of them. Okay, but here are the prefixes: hex for 6, hept for 7, oct, non, and dec. So I think there's a slide where we go over all of them, but let me just write it here just in case, just to make sure. Meth, eth, prop, but, pent, and then hex, hept, oct, non, and dec. These are the prefixes. So if I have a molecule that's 6 carbons, all right, and it's got a bunch of things hanging off of it, I know it's going to be some sort of hex. Okay, so these are things that you have to memorize because we're going to be using this so often, and this is kind of like, you know, a fundamental thing that people learn in organic chemistry. So meth for 1, eth for 2, prop for 3, but for 4, pent for 5, hex for 6. All right, hept, oct, like octagon, non for 9. That's easy to remember. It has ends in it, and then dec, like a decade, for 10. All right, most of you probably know probably half of these. Everyone probably knows pent, like a pentagon. All right, the pentagon's a 5-sided building. Some people usually know hex. I know hex. Here's how I remembered it. 6 has an X in it, just like hex. Hex is the only one that has an X, just like 6. So easy to remember, 6 hex. Hept is kind of weird. Some people want to say sept. They want to say septane. Do not do that. Do not do that. Okay, it's not a sept, it's a hept. Oct, people know octopus, nonane, N for 9, easy to remember, and dec for a decade for 10. All right, so like I said, half of these people usually can memorize or know automatically. You just have to memorize the other ones. Okay, some classifications of compounds: a primary carbon versus secondary carbon versus tertiary versus quaternary. However many carbons the central carbon is attached to is the classification of the carbon. However many carbons the central carbon is attached to is a primary, secondary, tertiary, or quaternary carbon. So if my central carbon is attached to only one carbon, if these are like hydrogens or chlorines or whatever else, an OH, right? This is a primary carbon because it's only attached to one carbon, okay? It's a primary carbon. This is a secondary carbon because it's attached to two carbons. So like, let's say I have a molecule, let me actually draw it out. Let's say we have a CH3, a C with a CH3 there, and an H, and a CH2, and a C, CH3, CH3, CH3. All right, a tertiary has 3 carbons attached to it, quaternary has 4. So if I look at this carbon right here, this carbon is attached to only one carbon. So this carbon is a primary. What would this carbon be right here? How many carbons is it attached to? 1, 2, 3. So it's tertiary. What about this one right here? That one would be secondary. How about this, 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 and this? Those are all the same. This is attached to one carbon, one carbon, one carbon. These are all primaries. One primary. And then finally this one, how many carbons is that attached to? That will be a quaternary. All right? Should be simple enough. Here's an example. Let me erase it. Hey, it's the exact same sample I used. Honestly, guys, I haven't even looked at these slides before that. I should have written these slides. All right, so here you go. Perfect example. Primary. Here's a secondary. It's attached to 2 carbons. All right, here's quaternary. This one is 4 carbons. That's 1 carbon. 2 carbons. 3 carbons. 4 carbons. All right, bond rotation. I just talked about this. These bonds freely rotate. Now, single bonds rotate. Once we get to double and triple bonds, those do not rotate. And so it makes a lot of those compounds very special. But single bonds do rotate. So you can kind of see, I can kind of take this and twist it and rotate it around in a circle. Okay? Now, usually, imagine this is a large group and this is a large group. If these are 2 large groups, which one of these structural or structures do you think the molecule would prefer? Where the 2 groups are as far away from each other as possible, or when these 2 giant groups are next to each other? All right, it's kind of obvious. I'm not trying to, it's not a trick question. Obviously, this is going to be the preferred molecule. You want these 2 groups as far away from each other as possible. And I believe they show you that in this picture, that these molecules have what's called a zigzag arrangement. Your carbons are going in a zigzag arrangement. Okay, so this is 4 carbons. All right, this is showing me a CH3 is attached to a CH2, is attached to a CH2, is attached to a CH3. This is telling me I have a CH3 attached to a CH2, attached to a CH2, attached to a CH3. Let me actually draw this differently just so it's purposely kind of. All right, so notice I have 2 big groups here that are kind of hitting each other. All right, these 2 big groups crowding. It's actually called steric hindrance. I don't know if we talk about it anywhere in the remaining of the chapters, but I've introduced a term. It's very easy to understand. Steric hindrance is the same thing as crowding. In this case, these groups are as far away from each other as possible. All right, so this is the preferred structure. That's why we draw these things in a zigzag form, okay, to kind of show this zigzag arrangement. All right, skeletal structures. I believe I've shown this already. A skeletal structure, this is the skeletal structure. It's a more simple structure. Basically, you have a carbon at each of these positions with its maximum number of hydrogens on it. Okay, so this carbon is going to have 3 additional hydrogens on it. This carbon has 2 hydrogens on it. This has 2 hydrogens on it. And this carbon is going to have 3 hydrogens on it. So that's kind of a shorthand. So if you want to do like a 6 carbon chain, 2, 3, 4, 5, 6, with let's say an ethyl group hanging off of there, And let's say we got a propyl group hanging off of there, and let's say we have a bromine that's hanging off of there. All right, so that would be the structure. All right, and the way that that would actually be would be a CH3 with a CH attached to a Br with a CH with a CH2, CH2, CH3 with a CH attached to a CH2, CH3, CH2, CH3. So this molecule is the same as that molecule, except it's in what's called a skeletal structure. All right, we can go over these. These do confuse people quite a bit. People are still trying to learn how to look at all the hydrogens and the carbons and all that stuff. So if it's easier for you to take something like this and just kind of put carbons here, like if you want to just, every spot has a carbon, I am fine with that. I want you to understand these structures. And then just know every carbon has to have 4 bonds. So if this is a primary carbon, because it's attached to 1 carbon, so I need 3 more hydrogens on it, which is a CH3. Okay. All right, we're going to stop right here because we will talk about 12.3 as a separate section.